So this video will be going through just some basics of recurrence relations for the core recursion and financial modelling unit of VCE Further Mathematics. So to start off with, just a recap of some of our key definitions. So a sequence is a list of numbers written in succession, and this can be a completely random sequence of numbers, so no pattern whatsoever, or it can have a pattern, or what we say is rule-based. And in further maths, we deal with rule-based sequences, so everything will have a pattern to it. Each of the numbers in this sequence is called a term. So if you're asked for the fourth term, you'll ask for the fourth number in the sequence. So we've got some examples here below. The first example there, you can see 4, 7, 10, 13, 16, 19. Indicates that we have a pattern there where the numbers are increasing by 3 each time. And so we have a special way of writing that pattern down as a rule, and that's called a recurrence relation that we'll look at next. The second one there, we can see 60, 30, 15. This time it's not a constant change, but it appears that we're dividing by 2 each time. So we're halving the numbers as we go. So again, it's following a rule or a pattern. And the third one, 10, 21, 43, 87, 175, might not be as easy to see, but the rule or the pattern we're following there is timesing by 2 and adding 1 each time. So as we said, the terms in the sequence, so if I was asked for the fourth term, we're talking about the fourth number along from our starting point. And so in further maths, we use recurrence relations to describe these sequences, these rule-based pattern sequences. Our first order recurrence relation is one that allows us to calculate what is the next term, given that we know the current one. So first order tells we can only ever work one unit in advance or one step ahead. In order for everyone to generate the same sequence from this particular recurrence relation that we write, there are two key things we need. The first one is what is the starting point, and we call that the initial term. And in further, we always state our initial term using a 0 or denoting it as a 0 in the subtext there. So you'll note in the rule here, we've got capital letters everywhere except for our lowercase n. So V0 represents in the sequence V, the 0 term or the initial term or the starting point is this. Then our rule is read as Vn plus 1, so the next term is equal to R times Vn plus D. So R, in this case, we use as a multiplier. We're always multiplying by something, and that generates a particular type of sequence. Vn is our current term. So think of n, the position in the term itself. So as n was 3, that would be actually the fourth number in the sequence, but term 3, and that would say we could use the rule to calculate V4. The plus D at the end is a constant value that can either be positive or negative. If it's positive, we're adding it. If it's negative, we're subtracting. Okay, so using that idea of reading our rule in words, if we look at the example here, I have V0 equals 1, where Vn plus 1 equals 5 times Vn minus 2. In words, that would mean the initial term or the starting point is 1, so that would be the first value I write down if I had to generate the sequence. The next term is equal to 5 times the current term minus 2. So in this case, that means my next term here will be 5 times 1 minus 2. So 5 times 1 is 5, minus 2, 3. To get the next term, I would be doing 5 times 3, so 15, minus 2, 13. To get the next term, 5 times 13, minus 2, and so on. So let's now have a look at some common exam questions where it just involves recurrence relations. More often than not, we are seeing that a question like this will occur either the first or the second multiple choice question in our exam 1. So we're going to have a look at a couple now just to give you an idea. The following recursion relation can generate a sequence of numbers. T0 is 10, Tn plus 1 equals Tn plus 3. So the number 13 appears in this sequence as, so it's asking you which position will it occur in. So if we were to write out that sequence, so we have 10, the next term plus 3, so 13, the next term 16, 19, and so on. And we can see here, we've already found the number 13. That is the second value that we've seen. But we need to remember, this first value, 10, we wrote down was T0. The next value is actually T1, T2, T3, and so on. So don't be tricked to thinking it's the second number I wrote down and picking up T2. The correct answer is actually denoted by T1. The next example is quite similar. A sequence of numbers is generated by the recurrence relation shown below. We have P0 equals 1, Pn plus 1 equals 3 times Pn minus 1. And what is the value of P3? So remember, if we were to write these out, P0 would be the first value, P1, P2, P3. So the answer we're looking for is actually the fourth number generated in this sequence. So if we're doing that by hand, we write down our first value is 1. 3 times 1 is 3. Take 1, 2. So we're going to write that little bit of working. 3 times 1 minus 1. Then we have 3 times 2 minus 1. So 5. 3 times 5 minus 1. So 14. And so there is the value that we want. That fourth value is 14. So our answer is C. We can also generate this sequence on our calculator. So let's have a look at that now. So when we're wanting to put a recurrence relation into our calculator and just generate a handful of terms, not a lot, but just a couple, we can enter this in a very similar way. So when we're looking at that rule where we had 1 as our starting point, so the first thing we're going to do is put 1 into our calculator and press enter or equals. And then we're going to use the ability to pick up a previous answer. So the answer component is going to act like the PN, the current term. So the rule that we had was 3 times our previous answer. So on our inspires, we would hit control and the minus sign to bring up that ANS answer. Then we're going to take away 1. So we're literally typing it in as we see it on the recurrence relation. So when I hit enter, it is picking up in my calculator the previous answer and dropping that or substituting in where we had answer written. So when I hit enter for a second time, it automatically picks up the 2 and substitutes it in here or drops it into that rule. So there I can do this in a bit of a quicker way than I did by hand, but it's up to you. You choose, do you do the calculations in your head by hand, or do you grab your calculator and do them in this quick way? So you can see there we arrive at the same answer. If I did need a couple of more values, I could just hit enter and it would keep generating them for me. I just have to keep count. This next example is a little bit different. So this time we're given a recurrence relation again where A0 is 3, AN plus 1 is given as 2 times AN plus 4. This time we're asked the value of A3 in the sequence generated by this recurrence relation is given by, and our options are a set of calculations. So this time, instead of finding the value of A3, we want to be able to find out, well, what little calculation would we do to get that? So the thinking can be very similar. Again, we could use the calculator and see when I hit A3, what did the calculator find for me, or what was the entry that it put in? If we were to do it here by hand, again, think about what are we generating? So A2, A3. So we want the calculation of that fourth value there. We're starting with 3 to get our next term, 2 times 3. plus 4, so 10. To get A2, we've got 2 times 10 plus 4, so 24, which means for A3, 2 times 24 plus 4, 52, but what we're concerned about is what was the calculation. So 2 times 24 plus 4 gives me D as the answer. Now, if you've got a question like that, but you weren't quite sure what they were asking, another option is to actually calculate each of these individual sums, each of the options. So you can just note down that we've got what value we've got there. So 4, 2, and 108. And if you're able to generate what the value of A3 is, then you can match your answer to the best calculation that's there for what you were able to achieve. This next example, we're now given a set of terms or a sequence and asked to identify which is the recurrence relation that would best suit these terms. So the first 5 terms given are 2, 6, 22, 86, 432. Sorry, 342. And so one of the first things I would be looking for is I can see that sequence is changing by various amounts each time. So it's not a constant change. So I can knock out option A because I'm not just adding 4 every time. But another way of doing it is simply to guess and check each of the 5 options. So write out the first couple of terms, maybe the first 3, and as soon as we get the correct 3 values, we can identify our answer. If we happen to get 2 that have the correct same first 3 values, then we might go to the 4th value just to check. And so here, if we're to look at option A, note here everything is starting with 2, and everything in our answer are also starting with 2. So if that wasn't the case, you could eliminate that answer. But here we would have 2, and then we're adding 4 each time. So 6, 10, 14, and so on. So that doesn't match what we need, so A is not an appropriate answer. B, again, we're starting with 2, times by 2 plus 2. So 2 times 2 is 4, plus 2 is 6. 6 times 2 is 12, plus 2 is 14. So not matching what we need, B is not an answer. For C, 2, and this time we're doing 3 times the current term. So 2 times 3 is 6, 6 times 3 is 18. Again, not what we need, we're looking for a 22 in that 3rd spot. So let's move on to D. We have start point 2, 4 times 2 is 8, minus 2, 6. 4 times 6 is 24, minus 2, 22. This is looking promising. So now 22 times 4 is 88, minus 2, 86. I think we're safe in saying this is our answer. 86 times 4 is 344, minus 2, 342. So pretty confident that's my correct answer. But when you're doing multiple choice questions, I want you to check every option, just in case you made a little calculation error, which led you to pick an early option that wasn't actually correct. So let's quickly do E. We're again starting with 2. 2 times 5 this time is 10, minus 4, 6. So 5 times 6 is 30, minus 4, 24. Doesn't match what we need in 22, so we can very safely say now that D is our correct answer. Our final example here. This time, consider the recurrence relation below, where we have B0 is 12, Bn plus 1 equals 2 times Bn minus 14. And we're asked which of the term of the sequence generated by this recurrence relation is the first to be negative. So which is the first to be a negative value? In this case, I'm going to use my calculator to help me out here and keep a track. Okay, so much like before, the first step is we're going to put in the value of 12 and hit enter, our initial term. Then we have the rule 2 times Bn, so 2 times and pick up our answer, minus 14. So we hit enter. So the B1 is 10, B2 is 6, B3 is minus 2. So there's our sequence there, 12, 10, 6, minus 2. And so the first value, remember our first term is B0, B1, B2, B3. And so bringing that information back, we can see that C is our answer there with B3. Okay, that is all as a quick introduction or recap of what recurrence relations are, and just to give you an oversight of how they will ask you questions about just the general recurrence relations in the exams. The next video, we will start looking at sort of some of the applications and the more specific things around linear and geometric recurrence relations and models.